Thank you so much for being here. I know it was a late night last night with the exam, so appreciate you guys being here bright and early again, although it's a little easier to get up and go when the sun is shining in the morning, isn't it? The exams, I think as Dr. Baker sent around an email, the exams, we're going to grade those maybe tomorrow, and the grades will be posted no later than Monday, so that's coming, and we'll hand those back to you next week in recitation. No homework due this week, so get a break there. And yeah, any other questions before we jump in related to the class or homework or the exam or anything? We all set? Okay, well today we're going to resume our discussion on chapter 19. I think we should be able to finish this up without too much problem and move on to chapter 20. So hopefully you got my email and were able to print off those notes sometime last night or this morning. So here in chapter 19, remember we're talking about two sample problems, and I'll do a little bit of review before we jump back into your notes. This is kind of building on the ideas that we saw at the end of chapter 18. So in chapter 18, at the end of chapter 18, we saw the idea of matched pairs, which is where we had two groups or two samples, but we were able to use sort of our one sample procedures because those samples were related or dependent. So remember there we took the difference between those two samples and then kind of proceeded as usual there. Here in chapter 19, we're going to take that sort of one step farther. Instead of assuming that we have two related samples, which applies sometimes but not always, we're going to see what we can do if we have unrelated samples or sort of independent samples that aren't connected in any way. Whereas in matched pairs we had sort of before and after on that was our two samples maybe. In 19 here they're going to be unrelated. So that's kind of the overall idea. And just our goal for this chapter, which we got into a little bit on Friday last week, is kind of the same goal we're going to have for the rest of this class. So the concepts we hit really hard with confidence intervals and hypothesis tests in chapters 14 through 18. Again, we spent so much time on that because we're going to keep doing that. So we're in a different chapter here now, but we're going to still be doing confidence intervals and doing hypothesis tests. And the usual thing with a confidence interval is we want to, here's our general form. We're going to take an estimate. We're going to add and subtract some margin of error, which, as you're used to the formulas by now, at some critical value. So far we've seen this has been a z star or a t star. And then we multiply it by the standard error, which is sigma over the square root of n, or s over the square root of n. Something like that. So we're going to kind of extend those ideas and see what these things should be in this chapter. So we want to construct confidence intervals, and we want to know how to do a test of significance. So figure out what our test statistic is, how do we calculate a p-value, and then we're kind of off to the races just like we were before. So again, this is the goal, kind of what we'll be doing in the rest of chapter 19 here, as well as in the next chapter and the rest of this class. So we're coming down the home stretch, yes, but a few more chapters to go yet. So picking up now in your notes, I think this is on should be on page 3 of your notes. Just to kind of remind you the connections between chapter 18 and chapter 19 here. So this first row here, this is chapter 18. So when we were trying to estimate a population mean, just one sample, we know our point estimate was, our estimate was x bar, and we had our standard error, and we could construct our confidence interval over here. X bar plus or minus t star times s over the square root of n. That's deeply in your brain right now, isn't it, from the exam? So sort of the corresponding idea, again, if we want to estimate the difference between, if we have a two-sample thing, we're going to estimate the difference between those two means. We're going to kind of do the corresponding thing. We're going to take x bar from the first sample minus x bar from the second sample. There's our formula for the standard error, which I'm not going to spend a lot of time discussing, and that will give us this formula over here. So we still have an estimate plus or minus a critical value times the standard error. So again, the formula is still the same. the general formula is still the same. We can just plug in sort of the details specific to what we have here. So the key is that we're gonna estimate the difference between the means of our two samples. It's kind of the main idea here. Kind of like with matched pairs, we're looking at a difference between our two samples. Here we're going to be doing the same exact thing. So that's our formula for the confidence interval. Same idea with the test statistic and kind of knowing what we're doing there. Again, the first line there is harkening back to chapter 18. That's familiar to you now. We're going to kind of do the same thing for chapter 19. And this is the kind of the usual idea of taking our value minus the mean divided by the standard error. So that's the same thing that we did before. We took x bar, we subtracted off the hypothesized mean divided by the standard error. We're going to do the same thing here, just what the standard error is changes a little bit. And maybe I'll just make a comment again here. So you can see that in the first line we're subtracting off mu 0. In the second line we're just subtracting off 0. And that's because our null hypothesis for this class will always be that the two means are equal to each other. So what we're going to assume and then kind of go from there is we're going to assume that the two populations the two samples have an equal mean. The two populations have an equal mean, and then kind of see if we have any evidence that that's not true. So again, we kind of have the same ideas. The formulas are going to change slightly. The context is changing, obviously, as well. But the same ideas that we saw before are going to be applying here. So kind of putting this together in one. This is at the bottom of page 3 now. Putting this together in one kind of bite here for you. We're looking at estimating the difference between two population means, mu1 minus mu2. We know how to estimate that and then do a confidence interval and a test statistic. Questions, comments you guys can think of on this, on the formulas anyway, the top half of this slide? Well, we'll get to an example here in just a second, but before I do that, just to maybe point out here is that I have a T star and a T. So that means we're still going to be working with the T distribution. So our critical value is a T, which means that we still have the T distribution, as is our test statistic. So good news is that when you're calculating T star and when you're calculating p-values, it's going to be exactly the same as what you did in chapter 18. So if you want a 90% confidence interval, you're going to go to table C just like you did before. When you want to find your p-value, also go to the table just like you did before and kind of find those bounds on what the p-value might be. So that's going to be exactly the same, but the one key difference is that the degrees of freedom should involve the smaller of n1 and n2. So these are the those are our sample sizes. So in the first sample we have we're going to say n1 individuals now. In the second group we're going to have n2 individuals, we'll say. And so when you're finding the degrees of freedom, remember degrees of freedom, again it was n minus 1. So now we'll take the smaller of n1 and n2 and subtract 1 off of that.
So whichever n smaller.
Yes, right. So whichever one of these things is smaller, take that one and subtract and use that as your degrees of freedom. So yeah, maybe let me write that down. So the degrees of freedom will be either n1 minus 1 or n2 minus 1, whichever is smaller. All right, and then just kind of at the top of page 4 on your notes, you kind of have a formal restatement of that, which again kind of gets at the conditions that we're going to be checking in this chapter. Those were given more formally in a list on the top of page 2 of your chapter 19 notes. So anyway, let's stop talking formulas and let's actually do an example here and show you how to apply these things. So our example here, suppose we have independent random samples of ticket prices for concerts from summer 2005, and we're looking at the Rolling Stones and Coldplay. So there was some discussion on who listens to the Rolling Stones anymore. I would object to that, but we'll assume we're back in 2005 when people still listen to the Rolling Stones. So we're going to assume that we have normality in our populations. And the questions we want to know is there evidence to suggest that the mean concert price is greater for the Rolling Stones than for Coldplay? And we will use alpha 0.05. So what is the what's the main thing that we need to do in this question? So the question asks us, is there evidence to suggest that the mean concert ticket price is greater for the Rolling Stones? So what kind of confidence interval versus hypothesis test, which boat are we sitting in here? And everybody said hypothesis test, right? Exactly. So when you see, is there evidence to suggest, that means you want to do a hypothesis test. Because you could just take the sample. I saw this on a few homework assignments I was grading for other recitations, and people just said, well, the Rolling Stones ticket prices is higher, so there is evidence, yes. But again, kind of the idea is we want to make sure to formally do a hypothesis test to say, is that difference big enough that we can say that there's evidence that it is actually greater. Okay, so again, kind of slowly stepping through how we're going to do these things. Again, kind of do the 4-step process here. Kind of to verbally restate the claim, we want to, the question we're interested in is the mean ticket price greater for the Rolling Stones than for Coldplay? So sort of our mathematical statement here can be, if we let's let mu sub r equal the mean Rolling Stones tickets. And again, we could say for 2005, we're going to be very careful. And we'll let mu sub c equal the mean ticket price for Coldplay. Just kind of setting up our notation there. So then this is kind of jumping ahead to what the alternative hypothesis will be, but how would we restate the question, the verbal restatement of the claim? How would we restate that mathematically using our symbols here? What's the question that we want to know?
Mu sub r is greater than mu sub c.
Exactly. Thank you, Alyssa. Yeah. So we want to know if the mean of the Rolling Stones tickets is greater than the mean of the Coldplay tickets. So again, in symbols here that we've set up, that's going to be that mu sub r, mu with the r subscript on it, is bigger than the mean with the c subscript on it. Okay, so now that we kind of have a clear idea, we're doing a hypothesis test. This is kind of the question that we're interested in answering. We can move on to kind of setting up what our hypotheses would be here. So again, we want to set up the null hypothesis, and we want to set up the alternative hypothesis. And we're involving the mean of Rolling Stones and the mean of the Coldplay tickets. So we need to figure out what our claim is. Again, the null hypothesis is always going to be that we're assuming these things are equal. So we're going to say, so if we're interested in seeing if one is bigger than the other, let's first assume that there is no difference between these two populations in their mean. And then see what evidence we have for the question that we're interested in asking, which is are the Rolling Stone tickets more expensive than the Coldplay tickets? So kind of taking that mathematical restatement and putting it in our alternative hypothesis there. So again, as usual, I think in these hypothesis test questions, the setting up the hypotheses can at least anyway be sort of the hardest part. Are we okay on where we got, on how we got here? Feeling okay? Okay, so now we're ready to, before we jump into doing our calculations and all those things, what's the next thing that we need to do? Check conditions. Thank you, Donna. Yes, so we want to check conditions. It's all of our favorite thing to do. So we still have the same three conditions. We have, do we have random samples? Is our samples, are they small enough? And then are they large enough? First one's easy, right? So the random samples one is often the one in class anyway. It's always most obvious. What do you guys think? Do we have random samples here? See some nodding heads again. Yes, we do. It's stated in the problem. So we're good to go there. Again, looking back to page 2 of your notes, the small enough sample says that we must have samples that are independent and from a large population of interest. So again, kind of like in chapter 18 when we had just one sample, we can look at, for both of our samples, we want to make sure they're both small enough. So 20 times N1, and we'll look at 20 times N2. So 20 times, first sample we had 12 Rolling Stone tickets, and we had 10 Coldplay tickets. So 240 and 200. Are there more than that many tickets for both of those groups? Of course there are, right? So both of these are less than all tickets from that summer 2005. So that's our small enough condition. We're good to go there. Our samples are not too big, but now we want to make sure they're big enough. And that's our large enough condition. Says we're now looking at the sum of the sample sizes. But the key thing here is that remember, if we have a normal distribution, if we have normal distributions, we're sort of good to go regardless of what the sample size is. So again, N1 equals 12 and N2 is 10. So N1 plus N2, we're looking at the sum there is 22. But we have a normal population. So again, in the question it said assume normality, so assume that our populations have a normal distribution. So when you have that assumption, we're good to go sort of regardless. Doesn't matter how big N1 and N2 are, we're okay to go. Yeah.
So would your sample size be 1, and if it's normal, you can still do this?
Absolutely, yeah. So the question was, if the sample size is 1 and we have normality, could we do this? And absolutely yes. Yep. In this chapter, when we're looking at you can't calculate a standard deviation of just one thing. So I guess technically yes, the answer to your question is yes, but usually you'll have at least 2 things in your sample. You need at least that many to calculate a standard deviation. But anyway, yes, if you have normality, it doesn't matter how small those N1 and N2 are, we're good to go there. So again, we've written out our conditions. We've kind of written out why they work out, and therefore we can proceed. We're good to go there. But good question. Any other question on conditions here? Again, same 3 as before. Now, just keeping in mind that we have two samples, so we need to, in the small enough, we need to look at both of those samples. Everybody okay there? Okay, so we put out what our hypotheses are. We made sure to check our conditions to make sure we can use these procedures. Since we can, we're ready to go, so we can next do our test statistic. So our test statistic, we're saying is t, and we're going to take x bar 1 minus x bar 2 minus 0, and then we're going to subtract, divide by, the square root of s1 squared plus s2 squared over n2. And again, you have the data right there in your notes, and it was on the slide where we introduced the example, so we can start filling these things in. So we have our x bar 1 is 325.5 minus 267.9. Then we divide by this ugly mess, which is 52.5 squared over 12. And our other standard deviation was 68.6. To square that and divide by 10, and take the square root of all of that. So in the calculation getting a little more tricky, but again, be very when you're entering this in your calculator, be very careful with parentheses and all that stuff. But so if you put that in, you should get this is 57.6 divided by the square root of 700.2835, we'll say, which is 2.177. So again, just taking the information that we have based from our data and plugging it into our formula. Here's our test statistic. Yeah, stop.
I think you already covered this, but can you tell me why we're minusing 0 again?
Oh, yes. Great question. So why are we subtracting off 0? That's a good question. So what we have here would usually be mu1 minus mu2, right? We're taking x bar 1 minus x bar 2. We're trying to estimate mu1 minus mu2. But remember, we're assuming that the null is true, and we're assuming that mu1 is equal to mu2. So sort of what we're hypothesizing for the difference between those two means is just 0. So if we're assuming that mu1 equals mu2, then this thing here is 0.
And it's just telling you mu is equal for the first one.
Right. Yeah. So we're kind of, again, remember, sort of the general conceptual thing with hypothesis tests here is we want to, whatever our question of interest is, we're going to sort of assume the opposite is true, and then kind of see what evidence we have for our sort of claim of interest being true. So we're going to assume that the null hypothesis is true. We're going to assume that mu1 is equal to mu2, and then kind of see what our data tells us about that. Very good question. Is that okay? Did everyone get that? That's why we have the 0 up there.
Does that mean eventually, later on in the course, mu1 isn't going to equal mu2?
Does that mean later in the course that you'll have something where mu1 is not equal to mu2? Is that so? Not for the purpose of this class. So for the purpose of this class, when you have a chapter 19, a 2-sample problem, we're always going to go with the null hypothesis being that those means are equal to each other. I realize I just kind of changed up notation on you here, so let me just say that mu1 is equal to the Rolling Stones mean, and mu2 is the Coldplay. Sorry to change that up on you. So just when I introduced the problem, I said mu r equals the Rolling Stones. That's going to be my first group. Coldplay is my second group. All right. So again, the actual calculation here is a little more involved, but the exact same idea, and we just can use our formulas for how we get there. Okay. So we have our test statistic t equals 2.177. kind of what we need to find is we need to find what our p-value is, and then we need to make our decision. So in order to find the p-value, again, we're kind of forget all of what we've done and just assume you're back in chapter 18. So we have our test statistic, and we need to figure out what our degrees of freedom are. So what will my degrees of freedom be here? Yes, exactly right. So I want to use a 10 because that's the smaller of. Again, n1 is 12, n2 is 10. So I want to put, since 10 is the smaller one, I'm going to throw that in there, and my degrees of freedom will be 9. Very good. So I'm going to kind of skip over going to the table, but again, you'll look in the degrees of freedom equal to 9 row, and we find that our t, the two numbers we can sort of sandwich that between is between 1.833 and the other number is 2.262. And what that tells us that our p-value is going to be between 0.025. Well, actually, before I do that, just to see if you're paying attention. So do I have a one-sided test or a two-sided test? One-tailed or two-tailed test here? Just a one-sided, right? Because my alternative back here, if I had a not equal to in there, then I'd have a two-sided. But because I have a greater than, it's just going to be a one-sided test. Very good. So then my p-value is going to be between 0.025 and 0.05. So again, my test statistic is sandwiched between the 1.183 and the 2.262. So I can trace that down to the one-sided test at the bottom of the table and find that my p-value is between 0.025 and 0.05. Okay, so again, got my test statistic, got my p-value. Next, I want to. What's my next step after I find my p-value? Yeah.
Deciding whether to reject or fail to reject the hypothesis.
Exactly right. So I want to make a decision, right? I want to either reject the null hypothesis or fail to reject the null hypothesis. And Donna, what am I doing here?
You want to reject it because your p-value is going to be smaller than 0.05.
Exactly right. So again, you compare your p-value to the significance level, which here we're using an alpha equal to 0.05. And we don't know what exactly what our p-value is, but we know that it's less than 0.05. It's between 0.025 and 0.05. So because this is the case, we reject the null hypothesis. Very good. And am I done? No. What else do I need to do? Interpret. Exactly right. That's the most important thing that we've done so far now is going to be to interpret this thing. So again, we can say because p-value is less than alpha equals 0.05, we reject the null hypothesis. And so what that means is there is sufficient evidence to conclude, and then we're going to kind of say what our alternative hypothesis is. So we're going to conclude that that Rolling Stones tickets are more expensive than Coldplay tickets. So again, because our p-value is smaller than our alpha of 0.05, we're going to reject the null hypothesis. And what rejecting the null hypothesis means is that that we can say there is sufficient evidence to conclude that Rolling Stone tickets are more expensive than Coldplay tickets. So again, kind of the exact same process that we've done before. There's just some slight differences in there with how we do our calculations. But then the p-value calculation is exactly the same. Conclusion is kind of exactly the same. We're going to be all set there. Any question you guys can think of on the hypothesis test here? That feeling okay? Ah, yes, someone's keeping me honest here. So what I should add on here is that, so what I should say is that from I should add that we are talking about summer 2005 here, so that's a good thing to add on there. So our conclusion sort of is, anyway, limited at least to 2005. Thank you for that. Thanks for catching me there.
Could you say like the p-value is less than or equal to the 0.05?
Yes. Yes. So again, we could have, again, if your p-value happened to be exactly equal to 0.05, then you would make the same decision here. So we could say less than or equal to. Probably won't have that be the case that it's exactly equal to 0.05, but if it were to happen to be, then
I just remember like even if it's equal to.
yes, exactly right. So right, of course, it is possible that your p-value is 0.05. So if it is exactly equal to alpha, our procedure is we're still going to reject the null hypothesis. Yeah, good question. All right, so that's how we're going to do a test of significance for this chapter. Yeah.
Do you have to include that that's an average? Did you just say that?
Also, probably something good to include. Yes. So the question was, should we say that this is an average? So we could say that the average Rolling Stone ticket price is more expensive than the average Coldplay ticket. And you guys are keeping me honest here.
Would that be points off if we didn't include average?
Would it be points off if you didn't include average? I would not take points off, so I think you're probably okay there. Maybe double check that with your TA since they're actually grading. But if you didn't say that on the exam, that's totally fine. Okay. So kind of continuing in this example, again, you can kind of think, so what we've said now from our hypothesis test is we've said that Rolling Stone tickets are more expensive, or the average Rolling Stones ticket price is more expensive than the average Coldplay ticket price. So that's not very satisfying, right? We kind of might want to know, well, how different are they? If the Rolling Stones is bigger, how much bigger are we talking about here? So that takes us to our idea of a confidence interval here. So what we want to do is construct a 90% confidence interval for the average difference in ticket prices. So we're not going to check conditions again. That would be redundant. So we'll say the same. So the conditions are valid from the hypothesis test from before. So we don't need to write those out again. So we're ready to go ahead and jump right into our calculations here. So our confidence interval, we're going to take x bar, we'll put an r there now to remind you what we're talking about, minus the average of the Coldplay tickets, plus or minus a t star times this big mess, the standard deviation of the Rolling Stones tickets squared divided by the number we have in our Rolling Stones tickets, plus the Coldplay group squared over the number of tickets from Coldplay. So I'm just throwing a R and a C in here instead of the 1 and the 2. And again, now it's just a matter of plugging these numbers in here. So this is 325.5 minus 267.9 plus or minus. Again, remember that our degrees of freedom here is we're going to take 10 minus 1 and get a 9 there. So if you go to the degrees of freedom equal to 9 row in table C and go over to a 90% confidence interval, you'll get that a t star should be 1.833 kind of skip over that for now as to how we got there. I'll let you practice that on your own. And we got to do this big calculation again, which we actually already did. So 52.5 squared over 12 plus 68.6 squared over 10. All that under the square root. And this is going to be 57.6 plus or minus 1.833 times the square root of 700.2835, which is 57.6 plus or minus 48.51. Which is equal to, again, we're working in dollars here, so $9.09 to $106.11. So we got our 90% confidence interval for the difference between these two ticket prices, average ticket prices, is that it's somewhere between $9 and $106. All right, so I'm not done yet, right? What do I need to finish this off with? Everybody said, nobody said, maybe. What? The usual thing we need to finish this off with an interpretation, right? So I'm going to put it right here so I have a little more space. So again, our interval was $9.09 to 106.11. So what we can say is that we are 90% confident that the average, I'll be a little more careful here, that the average Rolling Stones ticket cost between $9.09 and $106.11 more than the average Coldplay ticket. And we could tack on a from 2005 there. So again, kind of taking, again, the interpretation is a little more tricky now since we have this two sample thing going on here, but kind of just saying exactly what that means. We're 90% confident that the average Rolling Stones ticket costs between $9 and $106 more than the average Coldplay ticket from 2005. So again, remember in the hypothesis test we said that the Rolling Stones tickets are more than the Coldplay tickets, and now here we can say kind of how much more are they? They're between $9 and $106 more than Coldplay tickets. Any questions you guys can think of on sort of our procedure or the interpretation or anything like that here? I know it's early. Well, very good. So that's kind of the only example we'll get through in this chapter. Just to kind of give some closing comments, caveats, cautions is our usual favorite thing to end up with here. Is that if you again, so how we calculate our degrees of freedom when doing this by hand was just taking the smaller of n1 and n2 minus 1. Note that if you do this on using software, there's usually a more complicated formula for figuring out what the degrees of freedom are. So just noting that if you do these things in JUMP or some other technology, you might get an answer that's slightly different than what we calculated here, but it will be close enough, I guess, is the point. So if you're doing this in technology, you might get something that's slightly different than if you do it by hand. If you're looking in the text, there's this idea of using a pooled two-sample procedure. We're going to kind of ignore that for now. We're not going to spend a lot of time doing that. And then just finally, we prefer Usually, if you can, it's best to have equal sample sizes. So if you have any control over that, it's good to make, we would want N1 to be equal to N2. And it's good to kind of keep those conditions in mind, but the exercise from this chapter, we're going to assume that we have random samples and normal distribution. So it's good to kind of keep writing down what those conditions are just as a practice to say, oh yeah, I remember I need to check something before I can just blindly apply these procedures. But we're going to kind of give you those assumptions for most of the exercises in this chapter. So I think that brings us to the end of 19. Any kind of closing questions, comments you guys have on chapter 19 stuff? Okay. Well, then we're going to move on to chapter 20. Hopefully you guys were able to get those printed off and have them with you. Title here is Inference About a Population Proportion. And just kind of, again, we're kind of like we did in chapter 19. We're going to be doing the same thing, confidence intervals, hypothesis tests. Up until this point, so chapters 14 up through 19, we were looking at measuring a mean of some sort. So we were using our sample mean x bar to estimate something about our population mean. In chapter 19, we had two samples there. But suppose that instead of measuring a mean, I want to measure a proportion. So you can think of a lot of cases. It's election season. Election was yesterday, right? Maybe we want to estimate the proportion of something rather than the average of something. So kind of we're giving you some more tools for how to do the same thing, confidence intervals, hypothesis tests, but just when we're looking at a proportion instead of a mean. So as a sort of motivation here, thinking about why this is useful, why we care about doing this, going back to an example that we've seen before in this class, kind of our two-way table, where we're looking at the smoking habits of our sample here, as well as what their SES is, their socioeconomic status. And again, if you think about it, if we're trying to estimate something about this data, again, computing an average is sort of not what we need to do, right? I can't say anything about the average number of people who are, former smokers or something like that. So because I have a categorical variable, remember I'm looking at categories of things. It's not a numerical variable. I can't just compute an average. And then, of course, we have used this table to compute these probabilities, but we kind of want to take that a step farther here in this chapter. So again, what we're going to be using here is this thing called the sample proportion. So just like we had the sample mean from before, this what we're going to do is the sample proportion. So kind of the intuitive idea that you guys probably are okay with is that if I want the sample proportion, I'm going to take the number of successes in my sample and divide that by the total number of individuals in my sample. And successes here, this is kind of a success is whatever I'm interested in. So look at an example here in just a second, but just kind of keep in mind generically here that a success is whatever group I'm interested in out of my table. So again, the natural idea is I'm going to use this sample proportion to estimate the population proportion. And so sample proportion, again, remember has a little hat on top of it, just like, so again, we're going to call that P hat. We have more accessories for our letters there. It's not an X bar anymore, it's a P hat. And note that the number of successes is again, so if you want to get back to the number of successes, you can take P hat times the total number you have in the table. And then the last 2 points, I may put them on a separate slide here. Again, just to note that successes are sort of the event that we're interested in studying. So again, that will be specific to the example. And then just to point that could mean something like the rate of cancer or the rate of something else that's not at all a success. But we're going to still kind of use that language when we're calculating p hat. Or maybe we're looking at, instead of suicide, maybe we're looking at the number of shoplifting, the percentage of people who are shoplifters, right? We don't need to be so serious in this class. Okay, so using that language again, kind of what we can think about is like a question that we might want to answer is something like, what is the proportion of upper class volunteers who currently smoke? So again, thinking about that, back to that table, what is the proportion? What percentage of our upper class volunteers, or what percentage of people who are upper class are smokers? Again, we answer that question for the table, but if we want to kind of generalize that to the population at large, that's kind of our goal again here. So again, can we find a confidence interval? Can we do a significant test of significance, or a hypothesis test? It's kind of where we're going. So we'll just put question marks in here now, and that's what we want to figure out what those formulas are going to be, so we can answer these kinds of questions. So yes, we can answer all these. We can answer all these questions, and we're going to now figure out how we can go about answering those. Questions, comments you guys have so far? It's okay, kind of what the framework here is, what our context is. All right, I take your silence as that we're okay so far at least. So again, going back to chapter 11, again, kind of we're always building on what we've done before. Remember that if our individual observations have a normal distribution, we saw that our sample mean had a normal distribution as well. This was our sampling distribution here. And the good news here is that we have sort of a similar result for when we're working with a sample proportion. So what we have here is that kind of in our general setup, if we draw a simple random sample of size n from a large population with some true proportion of successes, so again, that's what we're trying to estimate. We're trying to estimate this true proportion. We're going to have a sampling distribution as well, and the mean of that sampling distribution is going to be the truth. So again, we're using p hat to estimate p. We're using the sample proportion to estimate the population proportion. And the good news is that our sampling distribution will be centered at the right value there. And then our standard deviation is going to be p times the square root of p times 1 minus p over n. And again, we're going to kind of gloss over where those things come from for the purpose of this class. You can take those as given. I'd be happy to show you where those come from if you want to come see me in office hours. So that's our mean and our standard deviation. And then if we have a large enough sample, so we're going to kind of be using the same idea as before, the sampling distribution will become approximately normal. So that this is kind of your key takeaway, is when your sample size is large enough, the sampling distribution of p hat will be approximately normal with mean p and standard deviation square root of p times 1 minus p over n. So kind of think about how this relates to what we did had on the previous slide. When we're looking at sample means, our sampling distribution ends up being normal. Same thing here if n is big enough, and just kind of what the mean and standard deviation are is different, but same idea here. So again, kind of remembering kind of exactly like we did before, the sampling distribution kind of tells us how x bar and now p hat what their behavior is. So once we have a understanding what that sampling distribution is, we can figure out what our confidence interval is here as well. So again, still the same thing. It's going to be our estimate plus or minus some margin of error. And whereas before it was x bar plus or minus t star times s over the square root of n. Sort of the corresponding thing here is we can take p hat plus or minus a z star times square root of p times 1 minus p over n. Again, remember we're trying to estimate p, which is the population proportion. So first of all, are we okay with this formula? Does it look familiar? Does it kind of see why that's what the formula should be? Yeah.
Okay, so if we're trying to estimate P, why is P in our formula?
Exactly right. So there is a problem with this formula, and that problem is that the formula includes P. So that's bad, right? So we're trying to estimate what P is, and here looks like we're required to use that in some way. So that's a problem. Yeah. But thankfully, we do have a workaround here. What we can do again is we can estimate. So, if our standard deviation is p times 1 minus p over n, what we can do is we can estimate that with the standard error, and we can just plug in p hat there for what p is going to be. So again, kind of like before, for means, the standard deviation was sigma over the square root of n, and our standard error was an estimate of that, s over the square root of n. Exactly the same idea here, is we can estimate that standard deviation, which will give us our change in terminology. We're going to call that our standard error. So then the formula that you can actually use is this thing down here, right? That formula, we have everything we can plug in and figure out what our confidence interval is going to be. And I think I have, yeah, so here's our sort of our formal statement here, is that if we have a simple random sample of size n from some large population, our approximate confidence interval is going to be p hat plus or minus z star times square root of p times 1 minus p over n. So some good news here, I think, is that note that I have a z star floating around there, right? So kind of going back to our back in those unrealistic chapters of chapter 14, when we assumed we knew what sigma was, we had a z star. Here, as the theory works out, we're going to assume that we can use a z star here for our confidence intervals. So when you're using a proportion, when you're doing a confidence interval for a proportion, we're back in that sort of familiar world where we have a z star, and it's not a t star. So we're going to be using. We're going to go back to table A, and your z star is going to be things like 1.645, 1.96, whatever your confidence level that you want to find there. Kind of go back to those familiar numbers. And then our little caveat down here is that we want to use this interval only when there are at least 15 successes and at least 15 failures. Which leads us to, real quickly, let me introduce our conditions for this chapter. So again, random sample, this is the top of page 4 now. Random sample and small enough sample, again, those are the same as they've always been. We want to make sure we have a random sample, or at least a representative sample from our population. We want to make sure our sample is small enough. We want to make sure the population is at least 20 times larger than our sample. And our large enough condition now is that we want to make sure we have at least 15 successes and at least 15 failures. And so what that means is we're going to have to check that both of these things are true. That n times p hat is at least 15, so that our number of successes is at least 15, and the number of failures, which is n times the proportion of failures, which is 1 minus p hat, is also at least 15. So I wanted to get through an example, and we did not do that. We're out of time. But we'll pick back up with this on Friday, and we'll actually do an example and actually apply this stuff. So Thank you guys so much for being here. I'm out of time. We'll see you Friday. Come see me if you have any questions. Otherwise, have a good rest of the day.